So elsewhere on my channel, I have 10 podcasts on the evolution of climate and socioeconomic scenarios, and I have maybe 20 podcasts on summarizing the IPCC AR6 report as well as AR5 report and so on. But in this context, we are just going to quickly look at some introduction to climate science, some introduction to climate and socioeconomic policies, scenarios, and then come back to adaptation before moving on to more about the economic principles for integrating adaptation into fiscal policies, right? Let me bring up the pointer here. Optimal adaptation. There is a large amount of adaptation to different climates across the world, but is this adaptation optimal? Basically, mitigation, as we said, is reducing greenhouse gas emissions and concentrations in the atmosphere by moving to renewables, electrical vehicles, carbon drawdown, bioenergy, and so on. Whereas adaptation tends to be very local, very region specific, and there is no blueprint. Each place has its own specific needs. So how do you even think about optimal adaptation? Are there any metrics possible to say we have optimally adapted and not done any maladaptation, for example, which is something we discussed before? Regions that are frequently exposed to tropical cyclones have adapted to at least some extent. For example, by developing early warning systems and advanced building codes. However, powerful storms inevitably cause damage and casualties, so there is always residual risk. Does that mean that they have not adapted? Should these regions have invested more in protection? So how do you decide between economic feasibility, cost-benefit analysis in the context of saving lives, or do you force people to move away from coastlines where cyclones are going to be a problem with increasing frequency, for example? Okay, so optimal adaptation has to worry about this. To answer these questions, it's necessary to adopt a normative principle. Without an optimality criterion, it's neither possible to take stock of the current situation nor to make policy recommendations. The chosen criterion should be transparent and consistently applied throughout government programs. This note argues that principles of welfare economics can be useful to guide policymakers on adaptation as for other development programs. So welfare economics is kind of assistance programs which raise a lot of debates by the rich against the poor, and people calling the community that's getting help as being lazy and this and that. So all kinds of nasty things happen. What to do, when and how, and what cost will ultimately relies on ethical choices, so-called normative principles of welfare economics, that should reflect the preferences of each society. How the society decides to protect its most vulnerable is often dependent on cultural memes and religions and other historical baggages. However, cost-benefit analysis, CBA, complemented by analysis and correction of distributional impacts, how the climate change impact gets cascaded through the society, can help decision makers maximize overall social welfare by avoiding wasting scarce resources. So it always comes back to worrying about money, right? This just cannot be avoided. To achieve this goal, it's essential that cost-benefit analysis is applied to adaptation as well as to all other development programs in a consistent manner. The difference between optimal and observed adaptation is defined as the adaptation gap. So you have to have an optimality criterion to which you compare the actual implementation of adaptation. So investment needs are estimated now based on the gap, and they vary depending on the normative criterion, how society decides to protect not just vulnerable human beings but also other species, ecosystems, biodiversity, etc. May even add non-market goods like well-being, health, and so on. Okay. So moving on to uncertainty in climate and socioeconomic scenarios. As I said, I've discussed these in quite a bit of detail elsewhere, so I'll just read off these here in this context. Even as strong climate trends are emerging globally, climate projections remain uncertain, especially at the local level. So I'll just tell you again, as I repeat many times, that the uncertainty in the climate projections are dominated by model biases, uncertainties, representation errors, etc. in the next 10 to 20 years. But beyond that, let's say from 2040 to 2050 and 2100, the uncertainties in the projections are dependent on how the scenarios are constructed. They assume population growth, GDP growth, transitions in energy, carbon capture, etc. So obviously those determine the plumes of ranges over which warmings are expected to happen, and then models have uncertainties in terms of translating the global mean forcings or global forcings of land use, energy transitions, radiative forcing from greenhouse gases, etc., into temperatures, rainfall, sea level, winds, etc. And some of these are in the Earth system models used to make these climate projections. Temperature, for example, can be done more accurately, but at a regional scale of, let's say, the Indian subcontinent, but not at a local scale. And this gets even worse for rainfall, for example. So these uncertainties have to be kept in mind while worrying about adaptation. How climate will exactly change at any given level of greenhouse gas concentration is uncertain. We just don't know that. But so are future emissions, impacts, economic growth, policy, technology, and other social developments. So the shared socioeconomic pathways we have discussed elsewhere worry about sustainability, regional conflicts, adaptation choices, development choices in terms of whether it will be fossil fuel based or whether it will go towards reducing emissions to meet the 1.5 degrees C or 2 degrees C target by 2100 above the pre-industrial level with some 67% probability and so on. The stringency with which we try to hit the target itself will determine these pathways, and the climate response is not linear. It can jump around as we increase greenhouse gases, especially the non-CO2 greenhouse gases and so on. So this gets fairly complicated in terms of the uncertainty in climate and socio-economic scenarios. Okay, so we have done lots of climate science in other courses, so in this context we'll just briefly read off the introduction as given by the IMF staff notes. The climate system is chaotic and hard to predict in the short term, but can be predictable in the long term. I don't know how much I want to get into this, but basically you have an intuitive sense that weather can be predicted for a few days, depending on whether you are in the tropics or mid-latitudes. Could be 3 days, 5 days, 10 days, but beyond 2 weeks it'll get chaotic because the so-called initial conditions used to predict weather, atmosphere is moves very fast, doesn't have much memory in terms of storing heat, so it goes chaotic. But on a longer time scale, like seasons to years, and with greenhouse gas forcing sometimes even into decades, various things are predictable because the ocean moves very slowly, ocean warms and cools very slowly, and so on and so forth. So just remember that if you don't know the details, you can follow up on my other courses. The long-term distribution of weather is called climate. So climate is what you expect and weather is what you get. Now I'm sitting here in July, it's a monsoon season, I expect rain, but it rained in the morning and now it's not raining, tomorrow may be sunny, and so on and so forth. So weather is what you get on a given day, but climate wise I expect monsoon to be rainy, right? Scientists use a 20 to 30 year time window to define the climate of a region, which is not a fixed window but depends on what you are interested in. However, for rainfall and extreme events, natural variability of weather can be mistaken for climate change. So separating climate change impacts on things that would happen during the monsoon anyway If rainfall is reduced, is it because of climate change or is it because of El Nino that is happening in 2023 and so on? Or, there is a detection aspect where you detect the change has happened in the rainfall amount. Then there is an attribution effect where you have to decide whether it was caused by climate change or just natural variability. Okay, attributing any extreme event to climate change is very difficult, especially because some things are just not captured by the model at a scale at which extreme event happens. Very heavy rainfall, even on a larger scale, is about tens of thousands of square kilometers, and rainfall may not be done very well at this scale. For example, 2022 Pakistan flood was fairly large scale, and some attribution exercise was done to say the probability of this flood was heavily increased by climate change. But there are a lot of interpretations involved there, and how do you say that? What is the confidence level in saying that climate change contributed? So these are tricky things. Attributing any extreme event to climate change is difficult. There are three sources of uncertainty in climate scenarios. The first is called internal variability and variability, and is due to the chaotic dynamics of the climate itself. It dominates the first 20 years of each scenario and can be quantified in probabilistic terms if data is available. Second is called model uncertainty and emerges because the exact functioning of climate system is unknown. We are valiantly building models, but there are many processes like cloud formation, rainfall production is not understood from first principles, so we empirically represent them based on data, and this is problematic. It's impossible to know with what probability each model is the correct representation of the true climate system. This is a cause of deep uncertainty, and it's usually the main source of uncertainty 20 to 50 years into the future, as I said already. Finally, scenario uncertainty emerges because the future concentrations of greenhouse gases in the atmosphere depend on future technologies, socioeconomic developments, and policy. As all these factors cannot be predicted in probabilistic terms, this is a second cause of deep uncertainty and becomes more important 50 years into the future. Okay, so the COVID-19 and invasion of Ukraine by Russia tell us how socioeconomics, geopolitics begin to affect pathways of human development, economy, energy use, etc. get impacted or perturbed. Climatologists use multiple lines of evidence, observations, models, theory, etc. to detect trends, to attribute them to climate change, and to make projections. Okay, so maybe I'll leave this here and come back and look at adaptation and sustainable economic development in the next podcast. So optimal adaptation is an ideal goal. Optimality needs a definition, and adaptation gaps have to be identified, and then action has to be taken. Policies have to be derived or developed to deal with reducing these adaptation gaps, remembering that there will always be residual risk, especially with emissions and greenhouse gases increasing and climate changing continuously. Okay, so let's leave this here.